Okay, so diving into a pretty cool area today where like AI vision's language, trying to build models that can really understand both. Now, the standard way of building these, what they call multimodal large language models or MLLMs, right? It's been this kind of modular design. You have a separate component, maybe like a vision transformer or VIT to deal with images. And then you have your trusty large language model doing its thing with text. And then the key is how do you bridge them? That's where you bring in the, what they call it, a modality connector.
Exactly. And that's been the dominant paradigm for a while now, this separation. But what we're looking at today is a paper that really flips that on its head. So it's asking this question. What if, instead of having this separate vision encoder, we try to build that visual understanding directly into the language model itself, especially during inference when you're actually using it?
Yeah, that's a huge shift. And that's exactly what we're going to be digging into, this whole idea of vision as LoRA, or as they call it, VoRA. And what really grabbed us about this approach is that core ambition to build visual capabilities directly into the LLM. We're moving away from that separate encoder.
Right. And to really get into the nitty-gritty of what makes this so innovative and impactful, we've been poring over some material. The Vision as LoRA briefing document, a really helpful study guide that goes along with it, and of course the research paper itself. Those are the bedrock of this deep dive.
Absolutely. So our mission today is to go beyond just scratching the surface. We want to understand how VoRA changes the game academically and especially zero in on those novel elements. Like, why could this encoder-free approach be so important for the future of MLLMs? We want to give our listeners a clear path to grasping this cutting-edge stuff.
I think that's key.
So let's get to the heart of it. What is VoRA doing differently in terms of architecture compared to what we've seen before?
Well, you hit the nail on the head when you mentioned the typical setup, right? You have your image processing handled by one network, and then you feed those features into the language model. What VoRA does is it injects these vision-specific LoRA layers, that stands for low-rank adaptation, right into the LLM itself. And the crucial thing is, during inference, when the model's actually working, you didn't need that separate vision encoder anymore.
Okay, so LoRA. Now, we've talked about LoRA in the context of fine-tuning these massive language models efficiently. But in VoRA, is LoRA being used to, like, enable the LLM to understand images?
Think of it like this. You're adding on this specialized visual processing module to the LLM. During pre-training, they introduced these trainable matrices, the LoRA layers, right into the LLM. And these layers are specifically geared towards learning how to process visual data. Uh-huh.
Okay.
But here's the critical part, and this is something the researchers emphasize. The original parameters of the LLM, that massive parameter space, they're frozen during this visual learning process. So the LLM retains its core language abilities, but simultaneously it's developing this new visual skill set.
So you're basically teaching it to see without messing with its existing language brain.
Exactly. And this has really interesting consequences for how we use these models.
Okay, I'm intrigued. How's up?
Well, here's the elegant part. Once you've trained those vision-specific LoRa layers, you don't keep them separate. Instead, you directly merge them into the weights of the base LLM.
Ah, I see.
So when you're using the model to make predictions, there's practically no extra computational cost, no extra memory footprint compared to the original LLM. It's if the LLM has inherently learned how to process images. And this efficiency gain is a big deal, especially when you think about real-world applications.
That's really neat. It's not just a different way of training, it's a fundamentally more efficient design, especially when you deploy these models.
Exactly.
Now, in the briefing materials, they talked about how VoRA tackles some limitations we see in the usual way of building MLLMs. Can you break those down for us, especially from a research perspective?
Sure. One of the biggest limitations Dore addresses is the issue of fixed resolution and vision encoders, particularly those VATs. They're typically trained on images of a specific size. So when you throw images at them that have different dimensions or aspect ratios, you often have to do pre-processing like cropping or resizing, and that can lead to losing some information or just making the pipeline more complex.
Yeah, that doesn't sound ideal. It's extra steps, potentially compromising the data. So how does VoRA's approach, where vision is built in, get around this?
Well, since VoRA incorporates visual processing directly within the LLM, it inherits this ability of LLMs to handle variable length sequences. Like, think about how language models work with text. They can handle sentences of all different lengths without breaking a sweat.
Right, right.
VoRA treats the visual information kind of similarly, so it can just naturally handle different image resolutions without needing all that pre-processing. That flexibility is a big win, both in theory and in practice.
That's super interesting. So it's more adaptable just by the way it's structured. Now, what about that whole processing workflow you mentioned earlier? That sequential nature seems like it could be a bottleneck.
Absolutely. When you have a separate vision encoder, the LLM essentially has to wait for the visual processing to finish before it can even start working with the visual features and generating a response.
I see.
VoRA, because it's so tightly integrated, has the potential to really streamline that. The LLM doesn't have to wait for an external component. It all happens internally. So you could potentially have a smoother, maybe even faster interaction between the visual and linguistic processing.
That makes sense. Okay, so potentially more efficient, simpler architecture, and able to handle variable image sizes. Now let's unpack some of the specific innovations within VoRA that they detail in the paper. One that jumped out was this blockwise distillation method. What's the big idea there?
Blockwise distillation is a really clever way to transfer visual knowledge into those LoRA layers we talked about. Basically, they use a pre-trained vision transformer, or VAT, a model that's already great at understanding images as a kind of teacher model.
Okay, so the VIT is like the experienced mentor showing VoRA the ropes of visual processing.
Exactly. But here's where it gets even more interesting. It's not just about matching the final output of the VIT. Blockwise distillation goes deeper. It looks at the intermediate representations within the VIT, what the model is seeing at different stages of its processing.
So it's looking at the entire process of understanding the image, not just the end result.
Right, and it pushes those LoRA layers in the early stages of the LLM to learn similar representations. So they use this metric called cosine similarity to measure how closely those intermediate representations in the LLM match up with those of the VIT.
I see. So it's learning the how of perception, not just memorizing a bunch of labels.
Precisely, and that's what makes it so powerful. It accelerates the training process and reduces the need for tons of visual data. It's a smarter, more efficient way to teach the LLM to understand images.
So why this block by block approach instead of just, matching the final output of the VAT? What's the benefit there?
Well, by aligning those intermediate representations, you're transferring more than just knowledge. You're transferring the VOT's inductive biases, basically the built-in assumptions and strengths that help it learn effectively. It's like teaching the fundamental principles of visual perception, not just specific examples, and that leads to much faster and more efficient learning for them.
Makes a lot of sense from a knowledge transfer perspective. Now, the other cool innovation was this bidirectional attention, specifically for the visual tokens. Can you tell us more about that and why it's different from how language models typically use attention?
You've hit on a key architectural difference. In a typical LLM, they use what's called a causal attention mask. What this does is, when it's processing text, it makes sure each word or token can only see the words that come before it in the sequence. This ensures the language generation flows naturally.
Makes sense. So it's about keeping things in order, like you were saying earlier. So how is VoRA changing this up for visual information?
Well, for the visual part, for those image tokens, they ditch the causal mask and use a bidirectional attention mask. It's like saying, hey, you don't have to just look back. You can look at everything at once. So every part of the image can see and interact with every other part simultaneously.
Oh, so it's processing the image more holistically instead of just going from left to right.
Exactly. And this leads to a much richer understanding of the scene. Like, if there's a person interacting with an object, the model's understanding of the person can be directly informed by the object, and vice versa. It captures relationships in a way that causal attention can't.
Sounds like a more intuitive way to process images where context is everything. Did the experiments show this bidirectional attention actually works better for vision?
Absolutely. They found that using bidirectional attention consistently led to lower training loss and, really importantly, better performance on a bunch of visual understanding tasks compared to using the standard causal masking. So there's clear evidence that it helps the model learn better visual representations.
So we've got LoRA for efficient integration, blockwise distillation for that knowledge transfer, and bidirectional attention for better visual understanding. It's a lot of interconnected parts. How did the results overall support this combined approach?
Yeah, the results section of the paper is where this all comes together. One really striking finding early on was that if you try to train the full LLM on visual data directly without using LoRA and freezing those base parameters, the training just collapses. They call it loss collapse. It highlights how important LoRA is to make this whole thing work.
Wow, that's really interesting. Like combining these modalities naively just doesn't cut it. So what other insights did they get from the experiments?
Well, they looked at the rank of those LoRA layers, the dimensionality of those trainable matrices, and they found that using a higher rank, like 1024 versus 512, usually led to better optimization during pre-training and distillation. It suggests that giving the LoRA layers more capacity helps them capture those fine-grained visual features.
Okay, makes sense. What about the impact of the bidirectional attention?
Yeah, like we said, it consistently led to better performance across the board, cementing its role in the effectiveness of VoRA.
And the blockwise distillation, did the experiments show that was the right way to go?
They did. It turned out to be much more effective than just distilling from the final layer of that teacher via T. It led to faster training and better performance, confirming that aligning those intermediate features is crucial for transferring knowledge properly.
It's not just about the destination, it's about the journey, right?
Exactly. And speaking of efficiency, they also looked at how well VoRA uses data.
Okay, that's a huge factor when you're training these massive models. What did they find?
Well, the combination of the bidirectional attention and blockways distillation, those two together allowed VoRA to reach similar performance with way fewer training steps than a basic VoRA setup. So not only do these innovations make the model better, but they also make the training process more efficient.
That's a big deal for scalability. So zooming out, how did VoRA actually perform compared to those established encoder-based MLMs?
They found that when they trained VoRA with enough extra data, it could go toe-to-toe with the encoder-based models. They specifically compared it to a model called LLAVA 1.5, which is considered a strong baseline in the field, and the results were comparable. So it shows that this new encoder-free approach can hold its own against the state-of-the-art.
That's really impressive. Okay, so VoRA is showing great promise, but like with any research, there are always limitations and open questions. What did the authors point out?
One thing they acknowledge is that right now, VoRA needs more pre-training data compared to the models that use pre-trained vision encoders. And the reason is simple. VoRA is learning visual features from scratch, whereas those other models start with a vision encoder that's already been trained on a massive amount of image data.
Like the difference between learning a language from scratch versus starting with some basic vocabulary and grammar.
Yeah, exactly. And another limitation is that VoRA doesn't currently have a way to compress those vision tokens. That means the input sequences for the LLM can get quite long, especially compared to architectures that use a vision encoder to reduce the dimensionality of the visual input. But they do suggest some potential solutions for the future, like using larger image patches initially or employing some sort of token pruning.
So optimizing that input length is on the to-do list. Were there any types of tasks where VoRA struggled, maybe more than others?
Interestingly, they found that it underperformed on tasks that require a lot of world knowledge, like recognizing landmarks or celebrities or understanding really specific details about things.
Huh.
They think this is more due to the specific data they used for pre-training, not a fundamental flaw in the architecture itself. They argue that using more diverse and knowledge-rich data could fix this.
So a data issue rather than an architectural issue. Looking ahead, what are some of the most exciting research directions that come out of this work?
Well, one big one is just scaling it up. What happens if you train a much larger VoRA model on a massive data set? Their hunch is that you could actually surpass the performance of encoder-based MLLMs because you're not bottlenecked by that separate vision encoder anymore. But of course, testing that requires a lot of resources.
So that potential for better performance at scale without needing a pre-trained encoder is a big question mark that needs answering. What else are they looking at?
They also want to explore those vision token compression techniques we mentioned earlier to make the model even more efficient. And a really exciting direction is extending VoRA to work with other modalities, not just vision. Like imagine adapting this distillation process to learn from audio data or 3D point clouds. You could potentially build incredibly efficient models that can handle all sorts of input.
It's like building a truly multimodal AI, not just vision and language.
Precisely. And of course, they want to tackle those world knowledge issues, finding ways to incorporate richer data during pre-training so the model can handle those more challenging tasks.
That makes sense. And finally, any thoughts on using VoRA not just for understanding, but for generating stuff as well?
Yeah, that's another cool avenue for future work. Since VoRA uses bidirectional attention for vision, which is also common in image generation models, and it keeps that causal attention for text generation, they believe it could actually become a unified architecture for both understanding and generating multimodal content. That would be a big step towards more versatile AI.
Really exciting stuff. So to wrap up this deep dive, what are the biggest takeaways about vision as LoRa, especially from a research perspective?
The key takeaway is that VoRA offers this brand new encoder-free architecture for MLMs, and it does it by directly integrating visual capabilities through those mergeable LoRA layers. And the big innovations are the direct integration, the blockwise distillation for transferring that visual knowledge, and that smart use of bidirectional attention tailored specifically for visual processing.
And all of that could have some big advantages both for researchers and for anyone using these models, right?
Right. Potentially much faster influence because you've merged those LoRa layers, a simpler, more elegant design because you've gotten rid of that separate encoder and connector, and more flexibility when you're working with different image sizes.
So taking a step back, what does VoRA tell us about the future of multimodal AI research? Is this a sign of things to come?
That's the big question, isn't it? Does this point to a future where models are more unified, more efficient, and can inherently learn to understand multiple modalities? Could this mean we move away from those external, pre-trained vision encoders? It's a really thought-provoking idea that could have a big impact on how we build and use AI in the future.
Really interesting food for thought. Thanks for guiding us through this deep dive. Until next time.